You know, when you take an antibiotic, have you ever really stopped to think about how incredibly smart that little pill is? How it wages this microscopic war inside your body with such surgical precision? I mean, really think about it. How does an antibiotic know to go after the invading bacteria, but leave your own cells completely alone? Well, that's what we're going to get into. Let's unpack the absolute genius behind these life-saving medicines. So, to understand how antibiotics work, you first have to know the enemy. And in the world of bacteria, it really boils down to two major categories. And the big difference between them is how they build their defenses. Think of it like armor. On one side, you have gram-positive bacteria. They have this single, super thick protective wall. On the other side are the gram-negative bacteria. Their wall is thinner, yeah, but it's got this extra protection from two outer membranes. This one fundamental difference in their armor, that is the key. It's the crack that antibiotics are designed to exploit. So the most direct strategy is pretty obvious, a full frontal assault. And that brings us to target number one, attacking that all-important bacterial cell wall. Okay, so here are the heavy hitters for that job. You've got penicillins, cephalosporins, and glycopeptides. Now, you'll notice some, like ampicillin, are what we call broad spectrum. They can hit both types of bacteria. But others, like vancomycin, are specialists. They only go after the gram-positive guys. So why is that cell wall such a perfect target in the first place? Well, this quote right here explains the bacteria's greatest weakness perfectly. The term is hyperosmotic. That's really just a fancy way of saying bacteria are so jam-packed with stuff inside that water is constantly trying to rush in and pop them like an overfilled water balloon. The only thing stopping that from happening is that tough, rigid cell wall. So when an antibiotic like penicillin comes along and shatters that wall, the bacteria literally just disintegrates under all that internal pressure. And here's the truly brilliant part. Our own human cells, we don't have cell walls at all, which means these antibiotics can wage a totally targeted war on the invaders, while our own cells are left completely unharmed. It is the perfect example of what's called selective toxicity. Now, for our next target. If you can't just break down the front door, you can always try to sabotage the factory from the inside. Target number two is all about wrecking the bacteria's protein production line. And these are the saboteurs. These classes of antibiotics, they sneak inside the bacteria and just jam the machinery of their protein-building factories, which are called ribosomes. You can think of a ribosome as being made of two parts that have to click together to work. And those are the subunits you see here, the 30S and 50S. So why doesn't this shut down our own protein factories? Well, once again, it's all about exploiting those tiny, tiny differences. You see, our ribosomes are built differently. They use larger parts, 40S and 60S subunits. The antibiotic molecule is shaped in a way that it only fits and blocks the bacterial machine parts, leaving our protein production to go on as usual.
Okay, on to another brilliant strategy. If you can't blow up the factory, you can always try to scramble the instruction manual. So let's look at target number three, messing with the bacteria's DNA blueprint.
The main players in this game are the quinolones, and their entire job is to stop bacteria from making copies of themselves. Because let's face it, if a bacterium can't replicate, a single invader can't turn into a full-blown infection. Okay, now what's really cool is how this works. A bacterium's DNA is this tightly wound-up circle. To make a copy, an enzyme called topoisomerase has to come in and carefully unwind it first. Quinolones work by just getting in the way. They block that crucial enzyme. The DNA stays locked up, replication grinds to a halt, and the bacterium basically hits a dead end. All right, our final strategy is maybe the most clever one of all. It's not about breaking things. It's about starving the enemy. Target number four is all about cutting off the bacteria's essential supply lines. And this is just fascinating. Bacteria have to create their own folate, which is a vital nutrient, just to survive. We humans, on the other hand, we get our folate from our diet, leafy greens and things like that. We don't even have the biological machinery to make it ourselves. So sulfonamide antibiotics exploit this difference perfectly. They block the specific enzyme bacteria use to make folate, which effectively starves them to death, while we, getting folate from our food, are completely unaffected. So we have these four brilliant strategies to fight bacteria, but the story doesn't end there. Because for every ingenious attack we design, the enemy is learning, it's evolving, and it's fighting back. And this brings us to the really crucial, ongoing battle of antibiotic resistance. The story of penicillin just illustrates this arms race perfectly. First, we attack. Penicillin has this thing called a beta-lactam ring that breaks the cell wall. But then the bacteria defend. They evolve an enzyme that destroys that very ring. So we counterattack. We create methicillin, a new drug designed to resist that enzyme. But then the bacteria evolve again, becoming resistant to even that, which leads to the infamous superbug MRSA.
And MRSA is a huge deal. This isn't just a stronger bug, it represents a major threat to all of modern medicine. It's a leading cause of dangerous hospital infections, and it's incredibly difficult to treat. It means routine surgeries or even minor wounds can become life-threatening. MRSA is a clear signal that one of our most powerful last-line defenses has been breached. The enemy is getting smarter.
So if there's one thing you take away from this whole explainer, it's this. Antibiotics are not just blunt instruments. They are masterpieces of targeted molecular warfare, meticulously designed to exploit the smallest, most subtle differences between bacterial cells and our very own.
They are an absolute testament to human ingenuity. But as this microscopic arms race continues, and as bacteria keep evolving, it leaves us with a really vital question for the future. As they get smarter, how will we?